Okay, moving on with matrix multiplication, what we want to do now is discuss some properties of matrix multiplication. We emphasized in the previous lesson that it's being a new sort of operation. Many things that would be considered trivial and that we know and use all the time with multiplication of numbers do not hold for matrix multiplication. So for example, it is not true that it's commutative. A times B is not necessarily equal to B times A, and we saw examples. For example, there's no cancellation. If you have AB equals AC, that does not mean that B equals C. You can't cancel out the A's, okay? So you have to be very careful and only do things with matrix multiplication when you actually know for a fact that they're true, that they hold. And the way to know is to write it as a theorem and go ahead and prove it. Okay, so that's what we want to do now. I just want to quickly remind you how we do matrix multiplication. So it's here on this board. So we have two matrices, A and B. They're column index of A, meaning the number of columns of A, has to match the number of rows in B. And so this is m by n, and this is n by L. And then the product is going to be m by L, the number of rows in A and the number of columns in B. The ijth element, the element in the ij position, the ijth entry in the matrix C in the product is obtained by multiplying the ith row of A times the jth column of B. So there's a lot of other stuff here and here, and here and here, which I didn't write. And all we're taking is the ith row of A times the jth row of B. So this is the first element here times the first one here, plus the second one here times the second one here, plus the third one here times the third one here. That's why we kind of indicated that we do it kind of like this. Okay, that's just to remember what we're doing. And all this sum of products is the single element sitting in the ijth entry here. And the way to denote it using sigma notation is that Cij is the sum of the products of Aik times Bkj, where k runs from 1 to n. Okay, good, everybody? Okay, so now let's write some properties of matrix multiplication. So this is actually a theorem. We're not going to prove all the properties. They're kind of similar. The proofs kind of get a bit boring. It's the same idea. We did a couple of examples for proving stuff about matrix addition. We'll do now a couple of examples, and you can practice the rest on your own. So part one, so maybe we should start by saying what are the sizes, so everything matches, because with multiplication it's important. So let A be a matrix of size m by n. B is going to be a matrix of size n by L. So is D. D is also going to be n by L, like B. And C is going to be L times Q, let's call it. Okay, so let all these be matrices. Then, so the first property is that we do have associativity. So if we take A, B, and C, and you can check that they match in terms of the dimensions. So this is m by n, this is n by L, and this is L by Q. So this equals A times B times C, whether we first do this product or whether we first do this product. So this is associativity of matrix multiplication. Property number two, distributivity of matrix multiplication with respect to matrix addition. So if we take A and multiply it by B plus D, both B and D are n by L, so they can be multiplied with A on the left. That equals AB plus AD. So this is the distributivity with respect to addition. Number three, distributivity the other way, and we have to mention it. because it's not commutative, right? We can't just say if it's distributive this way, then it's obviously distributive the other way. We'll just flip it, because multiplication is not commutative. Flipping it would not even work in terms of the dimensions. Okay? So if we take d plus b times c, and now that matches, equals dc plus bc. I don't know why I wrote d plus b rather than b plus d. That doesn't matter, right? They're the same size. It doesn't matter if I write d plus b or b plus d, right? Addition is commutative. Okay, good? Okay. Property number 4, how it relates to scalar multiplication. So if alpha is a scalar and we multiply it by a times b, that's the same as multiplying a by alpha and then taking the result and multiplying it by b. And in turn, it's the same as multiplying a by alpha b. So the scalar can move freely and multiply in whatever order you want. Note that in this line, in number 4, there's no symbol of multiplication anywhere, right? It's the empty symbol. But hinted here are 2 different multiplications. This is the product of a scalar times a matrix, and this is the product of 2 matrices. Okay, and both are usually denoted without any cross or dot or whatever. Okay, property number 5. Remember we had the identity matrix, which we denoted by I. I has to be of the appropriate size. I is always a square matrix. So if A is m by n, I is going to be I n, right? In order to be able to multiply. This equals I times A, and in turn this equals A. So I is indeed the identity with respect to multiplication. Okay, remember what I is? The ones on the main diagonal and 0 elsewhere, right? That's the identity matrix. Which I is it here? Here, A is m by n, and I'm multiplying it by something here, so this has to be im. So this and this are not the same I. This is an n by n matrix, the unit n by n matrix, with ones on the diagonal and 0 off diagonal, and this is the m by m identity matrix. Okay, so that's property number 5. Property number 6 involves the 0 matrix. The 0 matrix, which we just denote by 0, is a matrix of where all the entries are 0. And when you multiply by it, you just get 0. Okay? And the last property, which unfortunately I don't have space for on this board, but I really don't want to move it to another board, so I'll write it here. Property number 7. Property number 7. If you take the transpose of a product, that equals the product of the transposes, but in reverse order. So it's B transpose times A transpose. Remember, the transpose of a matrix is replacing the rows in the columns. Okay, the first row of A transpose is the first column of the original A, and vice versa. Okay, so these are the properties that do hold. Whatever's missing either does not hold or we didn't write it. I'm not saying that there aren't any additional properties, but of the basic ones, these are the ones that hold and you can use. Of course, you need to prove them. We're going to prove a couple. So let's start by proving property number 7.
Can I ask on the first property?
Yep.
Does it equal A times C with parentheses times B?
No, because that would be, the question is it the same as ACB? That won't even hold in terms of the dimension. You cannot multiply A times C, because A is m by n and C is L by q. They're not multipliable. Okay? Multiplication is only defined where the inner indices, the number of columns in the left one has to be equal the number of rows in the right one. Okay? So let's prove property number 7, for example. Let's prove that when we take a product and then take the transpose, it's like taking the product of the transposes, but in reverse order. Let's prove that. So, proof of 7. So remember, in proving that two matrices are the same, we need to prove two things. The first thing we need to prove is that they're the same in terms of the dimensions, that the dimensions match. The second thing we have to prove is that they're the same element-wise, that the elements match. And those are not necessarily the same thing. We have to do both. Okay? So let's start with dimensions. So sizes. Let's do it like this. Let's make a little chart like we did last time. So there's going to be the matrix, and then there's going to be the size. And we need to show that both sides have the same size. So the matrix A is an m by n matrix. The matrix B, we said, was n by L. Right? That's the data of the theorem. Those are the assumptions. So what is the size of A times B?
M.
Right, m by L. Okay, and therefore, what is the size of AB transpose?
L by M.
L by M, right. Okay, now what is the size of A transpose? N by M, right? B transpose is L by N, right? And therefore we can see that in fact we can only multiply them in the order B transpose times A transpose. It won't even be defined the other way. And the size of B transpose times A transpose is indeed L times M. Do you agree? And therefore they match. So the two sides of the equality that we're trying to prove indeed match in terms of sizes. So in terms of the dimensions, we're good. Now we have to prove the elements. So now we need to prove that the ijth entry of this matrix coincides with the ijth entry of this matrix. Okay? And if you're not yet used to that sigma notation, what we're going to do now is going to be extremely scary. But if you think about it and get used to the notation, you're going to see that in fact it's completely straightforward. Nothing miraculous is going to happen here. So let's do it. So elements, or entries. So let's look at the ijth entry of AB first. So AB, the ijth entry, is the sum of, let's call the elements of A by lowercase a's and the elements of B by lowercase b's. So this is the sum, k goes from 1 to n, of A, I, k, B, k, j. That's how we define the ijth entry of the product. Do you agree?
Yes.
Okay. Therefore, what is the ijth entry of the transpose? So AB transpose ijth entry. So it's going to be the sum, k equals 1 to n. And what do we need to take? We need to take the ijth, we need to take the AB transpose, right. So we need to take the jith element, the ijth element of the transpose is the jith element of this one. What's the jith element of this one? It's replacing j and I over here. Do you agree? So this is the sum, k equals 1 to n, a, j, k, b, k, I. Do you agree? This is nothing but the jith element of the product of A and B. It's the ijth element of the transpose. Do you agree? Everybody good? Okay, so this is this side. Now let's see what is the ijth element of B transpose A transpose. So what is the ijth element of B transpose A transpose? It's the sum of the ith row of B transpose times the jth column of A transpose. That's how we do multiplication. So what are the elements? Let's do it in two steps. So it's B transpose, the ikth element, right? These are precisely the elements in the ith row of B transpose times A transpose kj. These are the elements in the jth column of A transpose, right? And then the sum runs from 1 to k, 1 to n. Now what is this equal? What is the ikth element of B transpose? It's the kith element of B, right? So it's sigma k equals 1 to n, little b ki. And what is the kjth element of A transpose? It's the jkth element of A. So it's A, J, K. Good? And now, remember that these are just numbers. These are the entries. And for numbers, we do know the commutative law, right? So bki ajk is the same as ajk bki, right? So this sum and this sum are in fact precisely the same thing. Okay, so this and this are equal, meaning that the ijth entry of AB transpose is the same as the ijth entry of B transpose A transpose. Okay? Looks like a mouthful. It's kind of tedious. That's why I'm not doing all 7 properties. Okay? But that's the idea. Okay? And you can try carrying some more out on your own. Okay. Let's do just one more. The reason I want to do one more is because you don't always have to do it this way. Sometimes you can argue in a more straightforward way, which may look easier, but is not always convincing. This is as convincing as it gets. Okay, this is as formal as it gets. So for example, let's sketch the idea for the proof of, let's say 5. So 5, so proof of 5. 5 was the statement that if you multiply by the identity matrix, you get the matrix that you started with. So another way of doing these sort of arguments is, what is A times I? Okay, and remember that what we need, A was m by n, so we're taking I n. So we can just write what A is. What is A? A is A11, A12, A13, dot, dot, dot. A21, A22, A23, dot, dot, dot. A31, dot, 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 etc. Right? That's A. And what is I? So A, we can write here, A was m by n. And if we want to be even more precise, we can write where each of these ends. So it has m rows, so the last one here is going to be am1, right? It has n columns, so the last one here is going to be a1n. And down here, there's going to be amn. And now we don't even need to write m times n because it's explicit in the actual writing. Do you agree?
Yes.
Okay. And now what are we multiplying it by? We're multiplying it by the identity matrix of size n. So it's 1, 1, 1, dot, 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 1. And there are n. This is an n by n matrix, and all these are zeros. So let's write a giant 0 here and here for all the off-diagonal elements. Okay? And now what's the product? So the element in the 1, 1 entry, okay, is what? Is this row times this column. In this multiplication, A11 meets 1. All the rest of the elements are going to multiplicatively meet 0 and die. Do you agree?
Yes.
So all that remains is A11. What about the second one? It's this row times the second column. So A11 is going to meet 0, A12 is going to meet 1, and the rest are going to meet these zeros here. So the only one that survives is A12. Do you agree?
Yes.
Okay. And so on. Okay, so we get A back. Okay. Now why is this a bit less convincing than the previous way of proving? Because when I explained everything, it was clear what I was doing. But if you just read this, all I wrote is what I'm trying to prove. Right? I wrote A, I wrote I, and I said we got A, but kind of the details are missing. So if you want to call this a proof, you have to actually say that what I said as I did it. You have to say the ijth element is obtained by taking the ith row here and the jth column here, and in the multiplication, etc., etc., etc. Okay, you can't just leave it like this, because this is not saying nothing. It's just saying what you need to prove. Clear? Do you understand what the catch is? Okay, why you can't just write it like this? Okay. Okay, so this is A.
So word explanation is fine?
Hmm?
An explanation by words?
Of course. Any time in whatever argument you make, if you want to thicken it with words in English and explain what you're doing, that's completely fine, as long as you're obeying the overall rules of the game, which is you can only work with theorems and definitions, and your arguments have to be logical arguments that follow one from the other, but there's no reason not to just use words. That's fine. Many times, notation, which may be a bit heavy at first, like the sigma notation, but in fact, many times notation makes life a lot easier than just saying half a page of words. You just use the notation and it makes everything precise and much shorter, often. Yes?
Isn't this just the definition of an identity matrix? Like what you wrote?
This is the definition of the identity matrix. Okay?
But it's defined by the fact that multiplying by it gives you...
That's the motivation for this being the identity matrix. It's not the definition. The definition is this. An identity matrix of size n is a square matrix with 1s on the main diagonal and 0 elsewhere. That's the definition. What we proved is that it is indeed the identity for multiplication of matrices. Okay, it serves that role. Okay, just a remark, which is going to be useful later. So remember, we had the notion of a vector in this context. A vector was an array of elements, a matrix of size 1. There was a row vector, which is a matrix with only one row, and there was a column vector, which was a matrix with only one column. Okay? And this remark, which is not saying anything new, but only saying something that I want to kind of draw your attention to, because we're going to use it later, multiplication of a matrix. Let's remove this thing. A matrix by a vector, or a matrix and a vector, because it's a vector by a matrix and a vector, or let's emphasize a column vector, is just a special case of matrix multiplication. In other words, if this guy here, if the matrix B only has one column, then it's fine. You can still do the matrix multiplication and everything is defined exactly the same way. So it would be something of the form A m by n, A can be general, then B, this is going to be the column vector, so it's going to be n by 1, right? It's only going to have one column. And the result is going to be what?
N by 1.
N by 1.
Right, it's again going to be a column vector of size m, C m by 1. Do you agree? Okay, so this is just an observation because it's going to play a very important role later. So this is this discussion of the properties. What I want to do is a couple of kind of side kind of detours, things that we're going to use later on in the course, but that relate to matrix multiplication, and that's why I'm mentioning them here. So the first thing is powers of matrices. So what do I mean by that? So if A is a square matrix, n by n, then we define the following. A to the power 0, by definition, is the identity matrix. Okay? This should remind you of a number to the power 0 is 1, right? A to the power 1 is just A itself. Okay? And what is A squared, for example? It's just A times A. Okay? And A to the power 3 is A times A times A. Writing it like this is well defined because we know that it's associative. Okay? And so on. So this is how we define powers of matrices. Okay? Good? And it can only be defined for square matrices. Otherwise, the sizes won't even match. Okay? And the other thing that I want to mention, maybe we can erase here. Now that we know what powers of matrices are, what we sometimes do, and we may mention later on, is take polynomials and plug in matrices. So substituting a matrix into a polynomial. So suppose we have a polynomial. Let's just do an example. P of x equals what? 3x to the power 3 minus 5x plus 2. Here's a polynomial. And suppose we have a matrix. Let's take a nice and compact 2 by 2 matrix. Okay, has to be a square matrix. So P of A is replacing, substituting A in place of x. So what are we going to get? We're going to get 3a cubed minus 5a plus 2. So this 2 was actually 2 times x to the power 0. So here we're going to have plus 2i. This is now going to be a matrix. We're adding matrices. Writing just plus 2 is not well defined. What does it mean, a plus 2? Right? But what we really are doing is taking 2x to the power 0, plugging in a, so we have a to the power 0, which is I by definition. Okay? So this is now well defined by the definitions of powers of matrices that we had before. Okay? So this is P of A in this case, and we can calculate it in this case. So it's 3 times, so we need to do the calculations, right? We need, in order, A we know, I we know, we need to find what a cubed is in order to plug it here. So let's do that. And in order to find a cubed, I'm going to need to find a squared first. Okay? So a squared is a times itself. 1, 2, 0, minus 1 times 1, 2, 0, minus 1, which equals 1 plus 0. Do you agree that this is the first entry? And then 2 minus 2, 0. 0 minus 0, 0. And what are we looking? 0 minus 1 times minus 1, 1. So it turns out that the product of these two matrices is the identity, right? And now it's easy to find what a cubed is, right? We can say the answer automatically, because the identity times any matrix is itself. So a cubed is a squared times a. A squared turned out to be I, so it's IA, so it's just A. Do you agree?
Yes.
Okay. So here I'm going to write a cubed, but it turned out that a cubed is A. I don't know why I took this example. Anyway, 1, 2, 0, minus 1. This is a cubed. Minus 5a, 1, 2, 0, minus 1, plus 2i. Do you agree?
Yes.
Okay. And now we have to do multiplication of a scalar times a matrix, and then addition of matrices. Okay, so let's see what we get. Did everybody follow this? Can I erase this because it's kind of standing in the way? Good, everybody? Okay. So this equals 3.
Why you don't do 3 minus 5 and then, because it's the same matrix?
You're right. That would be a reasonable shortcut, but then I would have to erase the 3 and the 6. So I don't know what's more beneficial. Let's just do it. 3, 6, 0, negative 3, minus 5, 10, 0, negative 5, plus 2, 0, 0, 2, right? So that's the scalar multiplications. And then in turn, I have to add and subtract. So 3 minus 5 is negative 2 plus 2, 0. This one is 0 as well. And then we have 6 minus 10, which is negative 4. And here we have negative 3 plus 5 is 2. Plus 2 is 4. So this is what we get. So plugging in a matrix into a polynomial gives you a matrix, right? And that's the way it's defined. It's going to be useful later on. Okay, good, everybody? Okay, so this concludes the discussion of matrix multiplication, the real definition and how to work with it. Of course, you have to practice a lot. We mentioned that. And what we're going to do next is finally see some applications of matrices and how we use them. And I think the most famous application of matrices is in systems of equations. And that's our next topic.